Real numbers. Third part. Okay, let us move on to our next section, that is revisiting irrational numbers. Okay, we have studied two other sections in this chapter, that is at first section Euclid's division lemma and Euclid's algorithm, and what about our second section, the fundamental theorem of arithmetic and its applications, examples, etc. Then, next section is about the irrational number. That is, the first two sections are about rational family of real numbers. That is a particular number in rational family, that means integers. So, the first two sections concentrate on integer family which belongs to rational family of real numbers. Now we are moving on to irrational family of real numbers and its behavior, properties, etc. Okay. So for that, at first we are studying a theorem. Let P be a prime number if P divides A square, then P divides A, where A is a positive integer. What this theorem says? If P is, let P be a prime number. You should note this fact, P is a prime number. If P divides A square, then P divides A. That is, if P is dividing a square of an integer, then P is dividing its square root 2. Okay. Or if P is dividing square of integer, then P will divide that integer too. For an example, if 2 divides 36, then 2 divides 6 also. Similarly, what we can say? If, what can we say? If 3 divides 3 divides 81, then 3 divides 92. Okay. Then our first result in this chapter, that is, prove that root 2 is a irrational number. That is, at first, in previous classes itself, you have studied that root 2 is an irrational number. Okay. What we are going to do here, why root 2 is an irrational number? Because its decimal expansion is, decimal expansion is non-repeating and non-terminating. Okay. Non-recurring and non-terminating decimal expansion is for root 2. So, it is an irrational number. So, we are giving the proof of this formally in here. Okay. So, we are giving the formal proof of the fact that root 2 is an irrational number. So, for that, we prove this result by the method of contradiction. What does the contradiction mean? That means if we start for a journey and we have two paths in front of you, and the first path will lead to your destination, and second path is the wrong path. Okay, but if you travel by the wrong path, that is the second path, at some point you will find some mistakes or something wrong in that journey. Okay, if you find something indifferent or something wrong in that journey, then what we can conclude? Oh, this path is not the correct. Okay, this path won't lead to our destination, so we have to go by our first path. Similar way, we are going by a path, and whether we are checking that is a wrong path, and we are checking that whether we will find something wrong in that path here. If we find something unnatural, then we will conclude our path is wrong. So what is our path here? At first, assume root 2 is rational. If you go by that path, if we get something wrong in that path, we can conclude what? Root 2 is irrational. So we have two ways, okay, two paths. One thing, root 2 is an irrational number, and another thing, root 2 is a rational number. So we are moving by rational path and we are proving that path is wrong and which is the correct path. Root 2 is an irrational number. Okay. So for that, what if the root 2 is irrational? Rational, then root 2 equal to p by q, where p and q are integers and q not equal to 0. This every rational number can be represented like p by q. We are representing root 2 as p by q. And another important fact that is we are using for this theorem is that HCF of p and q equal to 1. That is the highest common factor among p and q equal to 1. So that p and q are co-prime. What do you mean by co-prime? Co-prime is any two numbers having HCF 1, that is 3 and 4. 3 and 4 has HCF 1, that is no common factors among them. So their HCF, that is highest common factor among them is 1. So 3 and 4 are known as co-primes. One more example about that, 130. Okay. So here P and Q are co-primes, that is least common factor among P and Q is 1. That is, or in other words, there are no common factors among P and Q other than 1. Then, what is next? We are taking Q to the left side, then root 2Q equal to P. Then squaring on both sides, what we will get? 2Q square equal to P square. Okay. So what we get? P square is a multiple of 2. So what we can conclude? Then 2 divides P square. Okay. If P square is a multiple of 2, then 2 will divide P square. That is, if 6 is a multiple of 2, then 2 can divide 6. Because 6 equal to 2 into 3. So 2 can divide 6. That is, if we divide 6 with 2, we will get a remainder 0. Similarly here, if we divide P square by 2, we will get a remainder 0. So 2 divides P square. Its P square is a multiple of 2. Then, by the theorem, what we can conclude? If 2 divides P square, then 2 divides P2. Okay. Therefore, 2 divides P. Then, what is next? If 2 divides P, what we can say as by here? P is a multiple of 2. So, what we can represent as P? If 6 is a multiple of 2, then 6 equal to 2 into 3. Okay. If 14 is a multiple of 2, then 14 equal to 2 into 7. Similarly, if P is a multiple of 2, then P equal to 2 into 6. Or we can do it by our division lemma. That is, if 2 divides P, then what will be our quotient is some C. And what is our remainder? 0. That is P equal to 2C plus 0. Which can be concluded from 2 divides P. Okay. Then if P equal to 2C, then what is? Then we are applying that result here. Then P square equal to P square equal to 2C whole square. Then 2Q square equal to 4C square. Okay. That is, here P square is transformed into 4C square. And now cancelling 2's in their terms, we will get Q square equal to 2C square. What which implies similarly we get Q square equal to 2C square. Then 2 divides Q square, or Q square is a multiple of 2, which implies 2 divides Q. That is, a Q is a multiple of 2. Then what we can write? Q equal to some 2K. Okay. Hence, what we got? 2 divides Q and 2 divides P. So what we get? 2 divides Q and 2 divides P. Hence, P and Q have a common factor which is 2. That is, highest common factor among P and Q is 2 or something greater than 2, not 1. Okay. That is, P and Q has a common factor which is 2. And why? 2 divides P and 2 divides Q. That is, if 2 divides 6 and 2 divides 24, 6 and 24 has a common factor 2. That may be its HCF or something greater than that will be its HCF, okay, which contradicts the fact that HCF of P and Q equal to 1. So what we assume, our assumption is that only common factor, that is highest among common factor among P and Q is 1. So we get one more common factor is there, that is 2. So our assumption is wrong. That is, what is our assumption? Root 2 is rational. So our assumption is wrong that root 2 is rational. So what we can conclude, root 2 is an irrational number. So which is the wrong or something unnatural we find in our path is that HCF of P and Q equal to 1 is according to our definition, but we got something that P and Q has a common factor other than 1, that is 2. Hence, what is our assumption? That is, root 2 is rational is wrong. So that path is wrong and we have to move by the first part. What is that? Root 2 is irrational. Hence, we can conclude root 2 is irrational. Okay, moving on to our next problem. Prove that root 3 is irrational. So in the previous question we have proved root 2 is an irrational number. Next is to prove root 3 is an irrational number. Okay. Similarly, we are moving, that is proof. We prove this result by the method of contradiction. Okay, for a small information, what is the method of contradiction is that if we have only two results in front of us, that is either this or that, then we will move by the method of contradiction. That is, for the real numbers, there are only two categories, that is either rational or irrational. If something is A is a real number, then A can be either a rational number or an irrational number. So we apply the method of contradiction. That is, we are moving in such a way that root 3 is a rational number. Okay, our assumption is that root 3 is a rational number and we are finding something wrong in our way and we will assume our assumption is wrong, then we will prove root 3 is an irrational number. Okay, so you must take in mind that is in order to move by method of contradiction, there are two and only two choices in front of us, either this or that. Okay. Next, we are moving as in previous question, that is, if root 3 is rational, then root 3 equal to P by Q, where P and Q are integers and HCF of P and Q equal to 1. That is where P and Q are coprimes. Coprimes are the number having HCF 1. Okay. Then, similarly, in the next previous problem, we are squaring. Then, 3Q square equal to P square by squaring on both sides. Okay. Then, what is here P? P square. P square is a multiple of 3 or 3 divides P square here. As in the previous problem, 2 divides P square here. What will divide P square? 3 will divide P square. Okay. 3 divides P square since P square is a multiple of 3. Okay. Then, what is by our theorem? If P square is a multiple of, if 3 divides P square, then 3 divides P. By the above theorem. Then what is P? P equal to, P is a multiple of 3, then P equal to 3C. Once again, why P is a multiple of, why 3 divides P, since P equal to, P is a multiple of 3. Okay, that is P equal to 3 into something. That is, if P is a multiple of 3 means 12 is a multiple of 3, that is 12 equal to 3 into some 4. Then what we can conclude? 3 will divide 12. Okay, here if 3 divides 12, what we can write? 3 divides P, then what we can write? P equal to sum 3 into C, that is 3 into a quotient C plus remainder 0. Then if P equal to 3C, we are applying this here, that is in P square, what we will get? 3Q square equal to 3C whole square. That is, instead of P, we are providing 3C whole square, which is equal to 9C square. Then on cancelling 3's, what we will get? Q square equal to 3C square. Okay, that is Q square is a multiple of 3, or 3 divide Q square from this step. Then what about by above theorem? By above theorem, 3 divides Q. Q is a multiple of 3. Okay, then Q equal to some 3C or 3K. That is, if 3 divides Q and 3 divides P, then what we can conclude? P and Q have a common factor, that is 3. That is, if P and Q have a common factor which is 3, then then our assumption is wrong. Why? We got something wrong in our way, that is HCF of P and Q is 1. Why we take HCF of P and Q equal to 1, but we got P and Q have other common factor which is 3. So HCF cannot be 1. It may be 3 or greater than 3, which is a contradiction to fact that HCF of P and Q equal to 1. So in our part, we have got something wrong here. So what we can conclude? Our path is wrong. That is, our assumption is wrong. Hence, our assumption is wrong. So what is our conclusion? Root 3 is an irrational number. Okay. So here we write by above theorem. In the time of examination, you have to mention which is that theorem. Okay, you have to write that theorem clearly in the time of your examination. Don't write by above theorem like that. Okay, you have to keep that in mind. So our next problem. Prove that 5 minus root 3 is irrational. So we are going to prove 5 minus root 3 is an irrational number. So what is our method? We will assume 5 minus root 3 is a rational number. Okay. That is, we are going to prove this by the method of contradiction. Then that is 5 minus root 3 is a rational number. That is, at first we are assuming 5 minus root 3 is a rational number. Then if 5 minus root 3 is a rational number, then what is 5 minus root 3? Which is equal to P by Q, where P and Q are integers, Q not equal to 0, and HCF of P and Q equal to 1. That is, P and Q are co-primes. That is, if P and Q has HCF 1, then they are known as co-primes. Then what is next? Okay. This is our common step. Then what is next? That is, we are rearranging this term like that. Rational numbers in one section and irrational in another. That is, 5 minus P by Q equal to root 3. Okay. Then what is that? 5Q minus P whole divided by Q is equal to root 3. That is, we are taking LCM, we will get this. So what is root 3? That is 5q minus p. That is the numerator is a integer and divided by q. Q is another integer. So root 3 equal to an integer divided by another integer where q not equal to 0. That is, from our result we know that q not equal to 0. Then what is root 3? Root 3 is a rational number. Why root 3 is a rational number? A rational number is something which can be written of the form p by q, where p and q are integers. So root 3 turns to be a rational number here. That is, we got an integer numerator by an integer denominator where the denominator not equal to 0. So what is our root 3? Root 3 turns to be a rational number. Whether it is right? It is a contradiction to the fact that root 3 is an irrational number. So our assumption is wrong. Why? We already proved that root 3 is an irrational number. So our assumption that 5 minus root 3 is rational is wrong. And we can conclude that 5 minus root 3 is an irrational number. So in examination point of view, if this question comes for more marks, that is more than 1 or 2, then you have to write the proof of root 3 is a rational number. Okay. More than 2 marks, then you must write the proof of root 3 is a rational number. Okay. Then our next question. Example 11, prove that 3 root 2 is irrational. Okay, we have to prove 3 root 2 is an irrational number. Similarly, we are proceeding by the method of contradiction. We prove this result by the method of contradiction. That is, at first assume 3 root 2 is a rational number. Okay, then what is 3 root 2? 3 root 2 equal to p by q. P and q are integers where q not equal to 0 and HCF of p and q equal to 1. P and q are coprimes. Okay, then what is 3 root 2 then? We are taking integers on one side, then that is 3 to the denominator, then root 2 equal to p by 3q. Okay, then here, as in the previous problem, root 2 equal to an integer p divided by an integer 3q. That is q not equal to 0. 3 also not equal to 0. That means 3q not equal to 0. So what we will get? Root 2 is a rational number. Why? Root 2 is equal to an integer by another integer. So what is next? Root 2 is a rational, which is a contradiction to the fact that root 2 is a irrational number. So our assumption is wrong, and what we can conclude? 3 root 2 is an irrational number. Similar way, if this question comes for more marks, you have to write the proof of root 2 is a rational number. Okay.